A staggering 4.2 light-years away lies Proxima Centauri, a red dwarf star unleashing destructive energy equal to 600 billion nuclear explosions every second. Orbiting this star is a planet that might support life, our closest potential new home in the cosmos. Yet the distance separating us from this world is so immense that reaching it would demand solving problems that strain the limits of physics, human psychology, and economic possibility. On such a journey, we would endure radiation storms capable of melting steel, encounter particles speeding through space with the force to obliterate entire cities, and face energy requirements so immense they would overshadow the total power consumption of our civilization. Prepare yourself for an unimaginable voyage. Like, subscribe, and join us to the end. Proxima Centauri is often described as our neighboring star, giving the illusion that it's just around the corner. This comforting phrasing hides a far more unsettling truth. Light, the fastest entity in the universe, still takes over 4 years to travel from Proxima to Earth. Traveling at 670 million miles per hour, fast enough to circle Earth 7 times in a single second, light still needs more than 1,500 days to reach us. To visualize this, imagine Earth as a marble in New York City and Proxima Centauri as another marble placed in the Pacific Ocean. The emptiness between them is a vast, featureless void, occasionally crossed by particles moving fast enough to puncture solid metal. Consider NASA's New Horizons probe, speeding through space at 36,000 miles per hour. It took 9 years to reach Pluto, yet even at that pace, it would need 78,000 years to get to Proxima Centauri, a duration longer than the entire span of human civilization. Even with our fastest rockets, the journey remains overwhelmingly slow. The stretch of space between us and Proxima is so enormous that 1 million solar systems could fit within it without touching. And distance is only the first challenge. The voyage would be hard enough if space were an empty road. Instead, the region between us and Proxima is filled with hazards that make the journey a brutal test of endurance and engineering. The 4.2 light-year distance equals 25 trillion miles. To comprehend this, imagine counting to 25 trillion, one number every second, without stopping for food, sleep, or rest. You would need 800,000 years. Walking that distance at 3 miles per hour would require 9 trillion hours of nonstop movement, over 1 billion years, longer than life has existed on Earth. Driving at 60 miles per hour, that would take 350 million years. In that time, the sun would orbit the galaxy 1.5 times, dinosaurs would rise and go extinct twice, and entire geological eras would pass. These comparisons reveal why astronomers use light years instead of miles or kilometers. At such immense scales, standard units lose meaning. The human mind cannot grasp such distances without analogies. But distance is only one obstacle. The mechanics of travel add another layer of difficulty. As we push toward higher speeds, the universe itself becomes the enemy. Voyager 1 launched in 1977, and now traveling at 38,000 miles per hour, would need 73,000 years to reach Proxima Centauri, if it were even heading in that direction. The Parker Solar Probe, the fastest spacecraft ever built at 430,000 miles per hour, would still need more than 6,000 years for the journey. Chemical rockets, used in all spacecraft so far, have fundamental limitations. The more fuel you carry, the heavier the spacecraft becomes, which requires even more fuel. This cycle makes interstellar travel nearly impossible with conventional propulsion. Ion drives are more efficient, but generate too little thrust, requiring centuries to accelerate to meaningful speeds. The energy required to accelerate just 1 ton to 10% of light speed is about 900 billion joules, more energy than humanity will use in 2,000 years. And that's only for speeding up. Slowing down at the destination doubles the requirement. Ideas like using magnetic fields or star-powered sails remain theoretical. Earth's energy production, every power plant, from nuclear to solar, generates around 28 trillion watts. Running every plant non-stop for 200 years would only produce enough energy to send a single ton of mass toward Proxima Centauri, assuming zero waste. That is the scale of the challenge. Because of this, most interstellar mission concepts focus on sending tiny payloads measured in grams. As for the cosmic radiation along the journey, the spacecraft would be bombarded for 4 straight years, exposing any human crew to lethal doses. The larger the spacecraft, the more fuel is required to accelerate it. This quickly creates a cycle that becomes unmanageable. Chemical rockets have strict efficiency limits, making interstellar travel nearly impossible. Even a massive rocket filled with the most efficient fuel could only propel a small payload to a fraction of the speed needed for practical interstellar journeys. Conventional propulsion simply cannot achieve the necessary speeds. For example, the Space Shuttle, which weighed 4.4 million pounds at launch, delivered only 250,000 pounds to orbit. This means 94% of its mass was fuel and engines, leaving just 6% for payload. Scaling this for interstellar travel would demand fuel masses larger than entire planets. Ion drives are more efficient but provide minimal thrust measured in ounces, not tons. They can accelerate spacecraft gradually over years, but even the best ion drive would require centuries to reach interstellar speeds, and the journey would still take millennia. The speed barrier highlights the limitations of carrying energy across light years. Sending even a small spacecraft to Proxima Centauri exceeds the total energy output of human civilization. Accelerating 1 ton of mass to 10% of light speed requires roughly 900 billion joules, equivalent to the energy consumed by the United States over 2,000 years. These calculations assume perfect efficiency, where all energy directly accelerates the spacecraft. In reality, engines lose enormous amounts as heat, light, and exhaust. Chemical rockets convert less than 3% of fuel energy into thrust, and even advanced ion drives operate below 50% efficiency. Accounting for inefficiencies multiplies the energy demands by tenfold or more. Energy needs double if the spacecraft must decelerate at its destination. Newton's laws still apply. A craft traveling at 10% of light speed would fly past Proxima Centauri in minutes without fuel to slow down. Some proposals suggest using magnetic fields or radiation pressure from the target star to decelerate, but these ideas remain theoretical. Most practical designs assume fuel must be carried for braking, doubling energy requirements. Earth's total energy production, from nuclear, solar, wind, hydro, and fossil sources, is about 28 trillion watts. Running all power plants for over 2 centuries would supply enough energy to propel just 1 ton to Proxima Centauri. This highlights the magnitude of the challenge. Consequently, interstellar mission concepts often focus on tiny payloads measured in grams rather than tons. Cosmic radiation further complicates matters, bombarding a spacecraft for 4 years and threatening any human crew. Outside Earth's protective magnetic field and atmosphere, cosmic rays streak through space like invisible bullets from exploding stars. These high-energy particles pierce spacecraft, equipment, and human tissue. Traveling near light speed, cosmic rays carry millions of times more energy than Earth-based particle accelerators. They can damage DNA, cause cancer, and induce radiation sickness that could be fatal within weeks. A crew traveling to Proxima would receive daily doses equivalent to full-body CT scans over 4 years. Solar storms intensify the threat, sending charged particles at millions of amp per hour. While astronauts in low Earth orbit have some shielding from Earth's magnetic field, interstellar travelers would face these storms unprotected. Radiation shielding is heavy. Lead works well, but weighs over 700 pounds per cubic foot. Surrounding a crew with 3 feet of lead adds thousands of tons to spacecraft mass. Water can provide protection while serving as drinking supply, but still requires substantial thickness. Additional mass increases energy needs, creating a vicious cycle. Some designs suggest using fuel tanks as radiation shields, effective only while full. As fuel is consumed, protection diminishes. Even robotic spacecraft suffer from radiation damage, affecting electronics, solar panels, and instruments. Interstellar dust becomes a deadly hazard at high velocities. Microscopic particles of silicon, carbon, and ice are harmless at rest, but at 10% of light speed, even a grain of sand carries energy comparable to a hand grenade. Pebble-sized objects could have the force of large bombs. Impacts follow Einstein's mass-energy relationship, where energy increases dramatically with speed. Even hydrogen atoms become dangerous projectiles that erode surfaces. Though sparse, roughly 1 particle per cubic mile, traveling billions of miles makes collisions nearly inevitable. Spacecraft must consider thick shields or electromagnetic deflection, but added mass increases energy needs. Higher velocities worsen the problem, with collisions comparable to nuclear explosions. Sparse hydrogen gas at relativistic speeds generates drag and extreme heating. Some proposals suggest clearing a path with lasers, but energy demands rival those for acceleration itself. These threats explain why interstellar mission concepts favor small, lightweight probes. Relativity turns interstellar travel into a journey through time. At 10% of light speed, time dilation is subtle. A 4-year journey appears slightly shorter to the crew. At 90% of light speed, time slows drastically. A journey of 4.5 years on Earth would seem only 2 years to travelers. At 99% of light speed, time aboard passes at 1/17th the Earth rate. Travelers would experience months while years pass on Earth, returning to a world that has aged 5 times faster, separating them permanently from the civilization they left. These relativistic effects create severe psychological challenges. Leaving Earth with a newborn could mean returning to find a middle-aged adult unfamiliar with you. Spouses and friends age differently, and crews become temporal exiles. Time dilation also complicates communication. Signals take varying times depending on speed, making conversations delayed or distorted. Observing Earth from a relativistic spacecraft, crews would witness rapid changes, from government shifts to technological evolution. Some scientists propose using time dilation strategically, letting crews experience short, subjective journeys while Earth gains decades to advance. Though multi-generational missions still face immense psychological and social challenges. Children born aboard these spacecraft would spend their entire lives traveling through the stars, never setting foot on a planet or breathing fresh air. These second and third generation crew members inherit a mission they never volunteered for, confined within a metal vessel, traversing vast emptiness toward a destination they may never reach. The first generation faces the trauma of permanent exile from Earth, watching their home shrink to a distant speck of light, knowing return is impossible. Every sunset, forest, and ocean breeze becomes a fading memory, lost amidst recycled air and artificial gravity. The emotional strain of this permanent separation could cause depression, anxiety, and breakdowns among those who initially volunteered, but now feel trapped by fate. Later generations would confront their own challenges. Children born on the spacecraft might struggle to understand weather, seasons, or open skies. Their environment would be limited to narrow corridors, small compartments, and self-contained ecosystems. They might develop claustrophobia, agoraphobia, or other mental health issues upon encountering a planet's vast surface. Over decades, social structures aboard the ship would shift unpredictably. Minor conflicts could escalate into enduring feuds, as the crew cannot escape one another. Divisions based on religion, politics, or culture could form factions vying for control of resources or the mission itself. Children born into these factions would inherit unresolved conflicts, potentially causing civil unrest within the spacecraft. The mission's original purpose might gradually lose significance. Great-grandchildren of the original crew could question why they continue toward Proxima Centauri or consider settling elsewhere, even on distant stars. Without a connection to Earth motivating them, later generations might abandon the journey or return home. Passing down technical knowledge poses additional pressure. Complex spacecraft systems require trained personnel to operate and maintain them. If key crew members die before training successors, critical systems could fail, endangering the mission. The psychological burden of maintaining the spacecraft in isolation would weigh heavily on those responsible. Some mission designs propose using artificial intelligence to monitor crew mental health and ensure mission continuity. Sustaining the crew over generations demands a fully closed system that recycles air, water, and food flawlessly. Every breath, drop of water, and calorie must be recycled perfectly for decades or centuries. Any failure in these systems could mean certain death in the void between stars. Air recycling systems must remove carbon dioxide while generating oxygen efficiently. Plants could help, converting CO2 to oxygen through photosynthesis. But cultivating enough plants requires large hydroponic farms with constant light, nutrients, and temperature control. The energy required rivals that needed to propel the spacecraft itself. Water recycling is critical, serving multiple purposes. The crew needs drinking water, and water also shields against radiation, cools equipment, and fuels thrusters. Advanced systems recover water from urine, sweat, humidity, and human waste, but these are energy-intensive and rely on delicate machinery prone to failure. Producing food in space is even more challenging. A balanced diet needs proteins, fats, vitamins, and minerals, which cannot be fully sourced from simple crops. Meat production is impractical, forcing reliance on plant-based proteins or synthetic alternatives. Nutrient deficiencies could cause serious health issues. The closed ecosystem must maintain perfect balance for generations without external input. Earth's biosphere supports millions of interacting species, creating stability. A spacecraft's ecosystem would likely contain only a few, making it vulnerable to collapse. Loss of one species could trigger a chain reaction, disrupting the entire life support system. Backup systems provide safety but increase mass and complexity. Chemical air scrubbers remove CO2 temporarily, but rely on expendable materials. Stored food and water sustain the crew in emergencies, but add weight, complicating propulsion. Some life support systems use synthetic biology or nanotechnology to enhance recycling, but these remain largely theoretical. As the spacecraft moves farther from Earth, communication delays increase. Signals between spacecraft and Earth could take years instead of minutes, making communication historical rather than real-time. Initially, delays are gradual, with radio signals taking up to 24 minutes between Earth and Mars. As the craft ventures further, delays grow to hours or days. In interstellar space, communication could take months or years. Messages from Earth might arrive after the crew has forgotten the original questions, and technical problems requiring ground support would be impossible to resolve in real time. Isolation from communication delays also affects crew psychology. News from Earth becomes less relevant as it arrives months or years late. Crew members might receive updates about loved ones who have long since passed, hear birthday wishes from people no longer alive, and follow humanity's progress through past snapshots. The inverse square law diminishes signal strength, making Earth transmissions weaker over light years, while spacecraft signals face even greater difficulty. Power limitations aboard the craft further restrict communication, especially beyond the solar system, where solar panels are ineffective, requiring nuclear power or alternative energy sources. These communication disruptions mean that crews on interstellar missions must resolve every issue independently, without the ability to call on assistance from Earth. Proxima Centauri proves to be a volatile, unpredictable star, regularly emitting radiation storms strong enough to sterilize planets and destroy spacecraft. Unlike the relatively steady output of our Sun, this red dwarf erupts with massive flares that increase its brightness tenfold or more within minutes. These sudden bursts release more energy than humanity has ever produced, sending deadly radiation throughout the Proxima system. Red dwarf stars burn fuel so slowly that they can shine for trillions of years, far outlasting our Sun. But this longevity comes at a price. Red dwarfs remain unstable and active throughout their long lifetimes. While our Sun occasionally experiences solar storms, Proxima Centauri remains in constant stellar turmoil, regularly erupting with flares capable of incinerating any approaching spacecraft. These flares accelerate charged particles to speeds so high that radiation levels in interstellar space seem mild by comparison. A spacecraft arriving during one of these massive flares would receive radiation doses equivalent to a nuclear explosion inside its crew compartment. Even robotic probes would face electronic malfunctions or destruction of critical systems. The planet Proxima b orbits just 4 million miles from its star, 20 times closer than Earth orbits the Sun. This tight orbit exposes the planet to the full fury of every stellar flare, without the protection of distance. The planet's atmosphere, if it ever had one, has likely been stripped away by billions of years of stellar bombardment, leaving a radiation-scorched wasteland. The star's magnetic field adds further complications for spacecraft attempting to enter the system. Charged particles trapped in these magnetic field lines create radiation belts similar to Earth's Van Allen belts, but thousands of times more intense. A spacecraft approaching Proxima would need to navigate these lethal radiation zones while contending with unpredictable stellar flares. The close orbit of Proxima b also suggests it is likely tidally locked, with one side permanently facing the star and the other cast in eternal darkness. The day side would experience temperatures high enough to melt lead. while the night side would freeze to temperatures colder than liquid nitrogen. Any potential for life would likely exist in the narrow twilight zone between these extreme environments. Even the timing of arrival could prove disastrous. Stellar flares occur unpredictably, and a spacecraft might arrive during a violent burst that could destroy it immediately. Mission planners would have no way to forecast stellar activity 4 years in advance, making every interstellar journey a gamble against cosmic forces beyond human control. But these hazards are only the final challenge in an already impossible journey. The propulsion technologies required to reach Proxima in the first place demand solutions pushing the limits of physics and engineering. Solar sails use the gentle pressure of starlight to propel spacecraft, requiring no fuel. However, the forces are so tiny that reaching interstellar speeds needs sails larger than entire cities. Light, though massless, carries momentum and exerts pressure on any surface it strikes. Solar sails harness this radiation pressure as wind powers a sailboat, but forces are millions of times weaker than even the gentlest breeze. A solar sail experiences just 9 pounds of pressure per square mile when facing the sun directly. This tiny force would never lift a feather on Earth. Yet, in the vacuum of space, even these small forces can gradually accelerate spacecraft to impressive speeds. The key is constructing sails with enormous surface areas while minimizing mass to create a favorable thrust-to-weight ratio. To achieve this, sails must be ultra-thin, often only a few atoms thick, made from materials like graphene or specially designed polymers. These sails can reflect sunlight while remaining nearly weightless, but they are extremely fragile. Even a speck of dust could puncture a sail, and solar radiation would degrade the material over time. The largest solar sails ever deployed span only a few hundred feet, but interstellar missions would require sails spanning dozens of miles. These massive structures must unfold perfectly in space, maintain their shape over decades of flight, and withstand impacts from cosmic dust and debris. The engineering challenges of deploying city-sized sails are unlike anything humanity has attempted. Solar sail acceleration diminishes with increasing distance from the sun. The gentle push near Earth becomes negligible beyond Mars, limiting acceleration to the inner solar system. A spacecraft using solar sails alone would accelerate for months or years while leaving the sun's influence, then coast at constant velocity for the remainder of the journey. More advanced concepts propose using powerful lasers to provide propulsion. Laser-driven sails could receive focused energy beams from Earth-based transmitters, allowing continuous acceleration long after leaving the solar system. However, maintaining precise alignment of the laser with the spacecraft's tiny sail presents immense challenges. A slight pointing error, a tear in the sail, or a malfunction in the alignment system could send the spacecraft off course and doom the mission. Despite these complexities, solar sails offer a critical advantage over other propulsion systems. Ion drives maximize fuel efficiency by accelerating individual atoms to extremely high speeds, allowing a small amount of propellant to power spacecraft for extended periods. These engines strip electrons from atoms of xenon or other gases, creating ions that are accelerated by electric fields to speeds up to 60,000 miles per hour. Ion drives are far more efficient than chemical rockets, achieving exhaust velocities several times faster, which translates to greater fuel efficiency. However, this comes at the cost of very low thrust. Ion drives generate thrust in ounces rather than tons, producing a gentle acceleration almost imperceptible to the crew. A spacecraft using ion drives might take months to break free of Earth's gravity, gradually building speed through sustained gentle thrust. This constant acceleration ultimately allows velocities that chemical rockets could never reach. Even with unlimited fuel, modern ion engines require substantial electrical power, often in the kilowatt range, necessitating large solar arrays or nuclear reactors. The Deep Space One mission, for instance, used solar panels the size of basketball courts to power a single ion engine producing only 2 ounces of thrust. Scaling this to interstellar speeds would require power systems comparable to entire cities. Advanced ion propulsion concepts suggest nuclear reactors or even fusion plants to generate the immense energy needed for high-thrust operations. These nuclear electric propulsion systems could provide thousands of times more thrust than current ion engines while maintaining exceptional fuel efficiency. However, building reactors capable of operating reliably for decades in space's harsh radiation remains a formidable engineering challenge. The brilliance of ion propulsion lies in approaching the theoretical limits of rocket efficiency. Unlike chemical rockets, which waste much energy heating exhaust gases, ion drives convert electrical energy directly into kinetic energy with minimal loss. This efficiency allows spacecraft to reach up to 10 to 20% of light speed, given enough time and power. Yet even the most advanced ion engines have fundamental limits that prevent relativistic speeds. Nuclear pulse propulsion, by contrast, uses nuclear explosions to accelerate spacecraft, detonating bombs behind massive shock absorbers that convert the energy into forward motion. Though it sounds like science fiction, nuclear explosions are among the most concentrated energy sources, capable of accelerating large spacecraft far beyond chemical rockets. Project Orion, seriously studied by NASA and the US Air Force in the 1960s, proposed dropping nuclear bombs behind a spacecraft and riding the explosions. Each detonation would strike a large steel pusher plate connected to the crew compartment via shock absorbers. Repeated explosions would gradually accelerate the spacecraft while protecting the crew from intense forces. The energy released by a single nuclear weapon equals thousands of tons of conventional explosives, accelerating massive spacecraft hundreds of miles per hour with each detonation. By chaining hundreds or thousands of explosions, spacecraft could theoretically reach significant fractions of light speed, enabling interstellar travel within a human lifetime. Nuclear pulse propulsion could carry far larger payloads than other methods. While ion drives and solar sails suit only lightweight probes, nuclear pulse systems could transport entire crews, life support, and scientific equipment. The pusher plates and shock absorbers add complexity, but the immense energy from nuclear explosions can move these heavy systems and payloads. Engineering challenges are enormous. The pusher plate must withstand repeated nuclear blasts without melting, cracking, or detaching. Shock absorbers must cushion forces that would otherwise crush the crew, while precise timing and placement of detonations is essential. Radiation from explosions poses severe risks, potentially harming both crew and equipment without massive shielding. Each blast generates electromagnetic pulses capable of destroying electronics, and neutron radiation gradually makes the spacecraft itself radioactive. Despite its potential, nuclear pulse propulsion faces environmental and political barriers. Detonating nuclear weapons in space violates international treaties, and radioactive fallout could contaminate areas near launch sites. Public opposition has so far stalled even modest nuclear propulsion programs. Yet nuclear pulse propulsion remains one of the few technologies capable of sending large crewed spacecraft to nearby stars within a human lifetime. Antimatter propulsion represents the ultimate goal. Matter and antimatter annihilate completely upon contact, releasing energy far exceeding nuclear explosions. A pound of antimatter reacting with a pound of matter would release energy equivalent to 43 million tons of TNT. This near-perfect energy conversion makes antimatter an ideal fuel, vastly more efficient than chemical or nuclear systems. Antimatter engines could, theoretically, achieve exhaust velocities approaching light speed, allowing relativistic travel within human lifetimes. Antimatter propulsion is theoretically near perfect, requiring only a few ounces to accelerate large spacecraft to 10% of light speed, reducing travel to Proxima Centauri from tens of thousands of years to mere decades. However, producing antimatter requires advanced particle accelerators, enormous energy, and currently yields minuscule quantities. Creating a single gram would need the entire US electrical output for thousands of years with current technology. Storing antimatter is even harder, requiring a perfect vacuum and magnetic suspension to prevent contact with matter, which would cause instant annihilation. These magnetic containers must function flawlessly for years or decades, as any failure could trigger an antimatter explosion capable of destroying the spacecraft. Annihilation reactions also emit intense radiation, necessitating massive shielding to protect the crew. Building engines that survive repeated antimatter explosions remains theoretical. Even tiny amounts are extremely dangerous. A few grams could power weapons far stronger than the largest nuclear bombs, raising serious security concerns. Despite these obstacles, antimatter remains the only known technology capable of rapid interstellar travel with manageable fuel quantities. Fusion ramjets, another proposed solution, would scoop interstellar hydrogen, fuse it, and use the energy to propel the spacecraft. But this concept remains theoretical and technologically unrealized. This concept eliminates the need to carry fuel for the entire journey, instead collecting propellant from space as the spacecraft travels between stars. The interstellar medium contains roughly 1 hydrogen atom per cubic centimeter, sparse by Earth standards, but potentially harvestable by a spacecraft equipped with enormous magnetic field generators. These electromagnetic scoops would stretch for thousands of miles ahead of the spacecraft, capturing hydrogen atoms and funneling them into nuclear fusion reactors that convert hydrogen into helium while releasing tremendous amounts of energy. A Bussard ramjet, named after physicist Robert Bussard, who proposed the idea, would accelerate continuously throughout its journey as it consumes interstellar hydrogen. The faster the spacecraft travels, the more hydrogen it encounters per unit time, increasing fuel flow and potentially allowing the ramjet to reach significant fractions of light speed. This self-feeding propulsion system could theoretically make interstellar travel practical. The magnetic field generators needed for hydrogen collection would dwarf any technology currently available. The electromagnetic scoop must span thousands of miles while producing magnetic fields strong enough to capture hydrogen atoms moving at millions of miles per hour. The energy required for these fields rivals that needed to accelerate the spacecraft itself. Nuclear fusion reactions demand temperatures of hundreds of millions of degrees and pressures found only in stellar cores. Controlled fusion on Earth remains an unsolved engineering challenge, despite decades of research and billions spent on development. Constructing fusion reactors that operate reliably in space while processing hydrogen collected en route represents an even greater technological leap. The ramjet concept faces a fundamental catch-22. The spacecraft must travel at relativistic speeds to collect enough hydrogen to sustain fusion. But achieving those speeds requires conventional propulsion, which faces all the fuel and energy limits discussed earlier. Detailed physics calculations suggest that at high velocities, ramjets might actually slow rather than accelerate. Drag from plowing through the interstellar medium at relativistic speeds could exceed the thrust produced, turning the ramjet into a brake that gradually slows the spacecraft to a stop in interstellar space. Yet, the concept continues to inspire variations that might overcome these limits. Breakthrough Starshot proposes building a laser system powerful enough to accelerate tiny spacecraft to 20% of light speed, using concentrated light beams to push ultra-lightweight probes toward Proxima Centauri in just 20 years. This ambitious project eliminates human crews entirely, focusing on miniaturized robots small enough to ride laser waves across interstellar distances. It requires constructing ground-based laser arrays with a combined output in the gigawatts, equivalent to several nuclear power plants operating simultaneously. These lasers would focus energy into tight beams to push spacecraft equipped with ultralight solar sails. The intense laser light would accelerate probes to incredible speeds within minutes, sending them on trajectories that reach Proxima Centauri faster than any other proposed mission. Each probe would weigh less than a gram, roughly the size of a computer chip carrying cameras, sensors, and communication equipment. These gram-scale spacecraft represent the ultimate miniaturization of space technology, packing instruments into packages smaller than postage stamps. Advanced manufacturing techniques borrowed from chip production could theoretically produce thousands of probes for the cost of one conventional spacecraft. The laser acceleration phase lasts only minutes, during which probes experience forces millions of times stronger than Earth's gravity. These extreme forces would destroy conventional spacecraft, but the tiny, lightweight probes can survive because acceleration is more evenly distributed across their small mass. The probes must maintain precise orientation during acceleration, keeping solar sails aligned with the laser despite forces that would rip larger ships apart. The laser system must track targets smaller than chips across trillions of miles while compensating for atmospheric distortion, Earth's rotation, and probe motion. Even a pointing error smaller than a human hair could cause the beam to miss entirely. The probes carry no fuel for deceleration, so they would zip past Proxima Centauri at 20% of light speed, gathering data during a flyby of only a few hours. Observations must occur autonomously, since radio signals take over 4 years to reach Earth. Communication presents its own challenges. Tiny probes cannot carry powerful transmitters and must rely on extremely weak signals. Ground-based radio telescopes would need to detect signals thousands of times weaker than current limits, assuming the transmitter survives the 20-year journey. Despite these hurdles, breakthrough Starshot represents the most realistic near-term approach to interstellar exploration. Suspended animation could transform the psychological nightmare of interstellar travel into a dreamless sleep, letting crews skip decades-long journeys and awaken refreshed at their destination. This concept borrows from natural hibernation seen in bears, ground squirrels, and other animals that slow metabolism during winter. Extending these processes to humans could make century-long voyages psychologically manageable. Medical researchers have achieved limited success with therapeutic hypothermia, cooling patients during complex surgeries to slow metabolism and reduce tissue damage. These procedures last hours, not decades, but demonstrate that human metabolism can be safely slowed under controlled conditions. Deep hibernation in animals slows metabolism by factors of 10 or more, allowing months without food while consuming minimal oxygen. Heart rates drop to just a few beats per minute, brain activity becomes barely detectable, and body temperatures approach freezing. These animals essentially pause life, emerging with minimal aging despite months of inactivity. Human hibernation research is still in its early stages, but scientists have identified some biological mechanisms controlling hibernation in animals. Specialized hormones trigger the response, and other biochemical changes protect cells from damage during long periods of reduced metabolism. Understanding and replicating these processes could eventually enable artificial hibernation for space travel in the docuverse. Suspended animation systems would need to keep crews in hibernation for decades while continuously monitoring their health and preventing emergencies. Automated medical units would supply nutrition, remove waste, and treat any health problems that arise during the long sleep. Life support must function flawlessly throughout the journey, since crew members cannot awaken to fix failures. The hibernation process carries medical risks, including heart issues, blood clots, organ failure, and potential brain damage. Current therapeutic hypothermia requires constant supervision, making multi-decade applications impossible without major technological advances. Waking after decades in hibernation presents further challenges. The human body would require careful rewarming, rehabilitation, and recovery from muscle atrophy, bone loss, and neurological changes to ensure readiness for planetary exploration. Some approaches suggest partial metabolic shutdown, keeping crew members in a twilight state between sleep and consciousness. Artificial intelligence could replace human crews entirely, deploying robotic explorers that never need food, air, or sleep, and can survive radiation doses fatal to humans. These machines can operate in vacuum without life support and remain functional for centuries. Advanced AI could make faster, more precise decisions than humans when facing unexpected challenges in interstellar exploration. Modern spacecraft already rely on autonomous systems for navigation, communication, and scientific research. Mars rovers, for example, operate independently for months, selecting targets and navigating with AI. Scaling this for interstellar missions requires AI capable of operating independently for decades. Robots can survive interstellar radiation without the heavy shielding humans need. Electronics can be hardened using materials and designs impractical for biological systems. Redundant systems can offset gradual degradation, allowing robotic missions to continue uninterrupted for decades. Removing life support drastically reduces spacecraft mass, improving achievable speeds or reducing energy requirements. Robots only need instruments, communication, and propulsion systems, maximizing mission efficiency. AI can also make optimal scientific choices during brief flybys of alien systems, processing information faster than humans and evaluating multiple options simultaneously. Developing artificial general intelligence for autonomous interstellar travel is still decades away, though current AI excels at specialized tasks. Creating systems that operate independently for decades while adapting to unforeseen challenges is one of computer science's greatest hurdles. Communication delays mean robotic explorers must act without input from Earth. A probe near Proxima Centauri cannot wait 4 years for instructions. AI must assess situations, weigh options, and select actions independently. Ethical programming becomes essential when robots operate beyond human oversight. Generation ships, massive vessels carrying thousands of people across interstellar space, would need to function as self-sustaining cities. These ships would include forests, lakes, farms, and infrastructure to support multi-century voyages. The smallest viable generation ship would need at least 10,000 people to maintain genetic diversity and preserve human culture. Artificial gravity is crucial, as prolonged weightlessness causes muscle atrophy, bone loss, and cardiovascular problems. The most practical solution involves rotating the ship to simulate gravity, but generating Earth-normal gravity requires mile-long structures. Structural stresses in rotating ships approach the limits of known materials. Advanced materials, like carbon nanotubes, could provide sufficient strength, though manufacturing mile-long structures remains theoretical. Closed ecological systems must function perfectly for centuries, recycling matter, maintaining atmosphere, and supporting plants and animals without external input. Any ecological failure could doom the population to starvation or suffocation. Social and political systems would evolve in isolation, potentially creating entirely new civilizations by the time the ship arrives. Descendants of the original crew might develop new languages, customs, and governance. These cultural shifts could complicate future communication with Earth. The economic cost of building generation ships would exceed the GDP of many nations. Constructing mile-long spacecraft requires millions of tons of materials, industrial capacity far beyond current levels, and labor forces comparable to massive infrastructure projects. In the docuverse, these ideas represent the edge of human ambition, blending biology, robotics, AI, and engineering to make interstellar travel possible. Each approach, from suspended animation to robotic explorers and generation ships, pushes the boundaries of science, revealing humanity's potential to explore the stars. The financial investment required to build generation ships may demand cooperation among multiple nations or a fundamental rethinking of how human civilization allocates resources. Yet, generation ships provide a unique advantage over other approaches to interstellar colonization. They offer the only realistic path for long-term human survival. The cost of interstellar travel is so immense that only the threat of human extinction could justify sending people to other star systems. Expenses for generation ships or advanced propulsion systems surpass the GDP of entire nations, requiring unprecedented international cooperation and strategic resource allocation. These vessels act as the ultimate insurance policy against cosmic catastrophe. Building a generation ship capable of transporting 10,000 people to Proxima Centauri would require mining operations of a scale far beyond current capabilities. The manufacturing infrastructure for mile-long spacecraft does not yet exist anywhere on Earth. Conservative cost estimates reach hundreds of billions or even trillions of dollars, representing a significant portion of global economic output. Such expenditures only make sense when weighed against the survival of humanity itself. Earth faces existential threats, asteroid impacts, supervolcanic eruptions, gamma-ray bursts, and AI-related risks that could end civilization within centuries or millennia. Investing trillions in backup colonies becomes reasonable when the alternative is total extinction. Economic reasoning for interstellar colonization mirrors that of insurance policies. People pay premiums to protect against rare but catastrophic events. Nations invest in defense against unlikely attacks, and interstellar colonies safeguard humanity from global extinction scenarios. Financial models for these missions must consider returns over centuries or millennia, with benefits accruing to future generations rather than original investors. Traditional economic analysis fails for century-long projects aimed at existential risk mitigation. International cooperation is essential for realistic interstellar colonization. No single nation has the resources to build generation ships or advanced propulsion systems, and maintaining political collaboration over centuries rivals the technical challenges of space travel. Economic interests, political disputes, and leadership changes could derail projects long before ships reach their destinations. Private funding may contribute, as wealthy individuals and corporations recognize the long-term value of species survival. Entrepreneurs who have created trillion-dollar companies might see interstellar colonization as the ultimate moonshot project, worth pursuing even without immediate returns. Yet private funding alone cannot cover these enormous costs. Humanity's commitment to its survival ultimately determines progress. Proxima b presents extreme conditions. One hemisphere endures eternal daylight, while the other suffers permanent night, creating an environment unlike anything in our solar system. The planet orbits so close to its red dwarf star that tidal locking forces the same side to always face Proxima Centauri. The day side reaches temperatures high enough to melt lead, with surface conditions capable of vaporizing spacecraft. Stellar radiation bathes this hemisphere in energy surpassing Venus, producing superheated rock and possibly molten lava flows. Any atmosphere on this side would be stripped away by intense stellar wind. The night side is equally hostile, with temperatures approaching absolute zero, freezing carbon dioxide and nitrogen into solid ice. This frozen wasteland is as lifeless as Pluto, lacking energy sources to support biology. Spacecraft operating here would face challenges similar to the outer solar system. Between these extremes lies a narrow twilight zone where temperatures might allow liquid water to exist. This strip represents the only potentially habitable area, yet it experiences hurricane-force winds as hot air from the day side rushes to the cold night side. Atmospheric circulation could reach hundreds of miles per hour, making landings extremely dangerous. Stellar flares from Proxima Centauri would intermittently sterilize any surface life with high-energy radiation. Potential life would need to shelter underground or underwater to survive these events. Proxima b's magnetic field, if it exists, is weaker than Earth's, offering minimal protection. Without adequate shielding, stellar winds would erode the atmosphere over billions of years, possibly leaving only a thin layer or none at all. Despite these challenges, Proxima b is the best candidate for interstellar exploration due to its proximity and rocky composition. Radio waves, traveling at light speed, could announce humanity's arrival years before spacecraft reach the system. Carefully crafted electromagnetic signals could convey human civilization, scientific knowledge, and peaceful intentions to any intelligent life. Powerful transmitters on Earth could broadcast messages detectable across interstellar distances, assuming alien civilizations possess radio telescopes comparable to our own. This implies that advanced civilizations near Proxima Centauri could potentially receive and interpret radio messages sent from Earth using current technology. The content of these messages must be carefully designed to ensure comprehension by non-human intelligence. Mathematical principles such as prime numbers or geometric relationships may serve as universal languages recognizable by any scientifically advanced civilization. Even the Drake equation, which estimates the probability of extraterrestrial intelligence, could be encoded to demonstrate human scientific understanding and awareness of other possible civilizations. Encoding knowledge into radio signals poses intriguing challenges that reveal the assumptions in human communication. How does one convey color to beings perceiving different light wavelengths? How is music explained to creatures without auditory systems? Creating interstellar messages forces consideration of which aspects of human experience are universal versus culturally specific. Timing signal transmissions is critical when coordinating radio messages and spacecraft arrivals. Signals sent today would reach Proxima Centauri in just over 4 years, whereas spacecraft with current propulsion require tens of thousands of years. Advanced propulsion could reduce travel to decades, aligning radio messages and physical missions within the same historical period. Multiple transmissions enhance reliability against technical failures or atmospheric interference, increasing the probability of successful delivery and demonstrating human persistence in establishing contact. Interstellar radio communication requires manageable energy compared to spacecraft propulsion, making it a cost-effective initial step toward contact. However, radio signals expose Earth's location and capabilities, necessitating backup plans for interstellar missions. Redundancy is essential. Multiple spacecraft, redundant systems, and alternative destinations ensure some missions succeed despite decades-long journeys and vast distances. Launching multiple generation ships at different times increases the likelihood of success despite technical failures, navigation errors, or space debris. Backup destinations safeguard against uninhabitable or hostile worlds. Recent exoplanet discoveries include potentially habitable planets like Tau Ceti, Wolf 359, and Gliese 667c. Pursuing interstellar missions to multiple destinations simultaneously mitigates risks if Proxima b proves uninhabitable or individual missions encounter obstacles. Diverse propulsion technologies, nuclear pulse, ion drives, solar sails, and fusion systems reduce reliance on a single approach. Robotic precursor missions can scout potential worlds decades ahead, providing critical data on local conditions. Small probes using laser propulsion could arrive within 20 to 30 years, mapping environments, radiation, and resources, allowing human crews to target the most suitable destinations. Communication relay networks positioned between Earth and interstellar missions maintain contact, coordinate multiple spacecraft, and provide redundancy if primary systems fail. Automated manufacturing aboard spacecraft enables production of spare parts and equipment during the journey, reducing reliance on Earth-supplied components. 3D printing and robotic assembly can create everything from electronics to structural materials using onboard resources or harvested asteroid materials. The ultimate backup strategy is establishing self-sustaining human populations across multiple star systems rather than relying on single colonies vulnerable to local catastrophes. The long journey to Proxima Centauri represents humanity's only long-term strategy to survive cosmic threats capable of ending our species within centuries or millennia. Earth exists in a perilous universe of asteroid impacts, supervolcanoes, gamma-ray bursts, and other catastrophic events responsible for mass extinctions. Self-sustaining colonies around other stars would preserve human civilization even if Earth becomes uninhabitable. The dinosaurs ruled for over 160 million years before an asteroid abruptly ended their dominance, illustrating the suddenness of cosmic disasters. Humanity without interstellar colonies remains exposed to single events capable of wiping out every human, ending billions of years of evolution. Developing interstellar travel would revolutionize human civilization beyond survival. Engineering generation ships, fusion engines, and life support for century-long voyages would drive rapid advancements in energy production, materials science, artificial intelligence, and closed-loop ecosystems. Becoming an interstellar species could transform humanity's perspective on its place in the universe, fostering a deeper understanding of our role and potential within the cosmos. Political disputes over borders appear insignificant when measured against the vastness of light years. Environmental challenges that now seem insurmountable could be addressed with technologies adapted from spacecraft life support systems. Interstellar exploration would compel humanity to plan across centuries instead of election cycles. Scientific discoveries made during these missions could answer profound questions about the nature of life, intelligence, and consciousness in the universe. Detecting life around other stars would confirm that biology is a universal phenomenon, not a cosmic accident unique to Earth. Encountering alien civilizations would radically expand our understanding of intelligence, technology, and the potential trajectories of advanced species. The economic returns from interstellar colonization could eventually justify massive initial investments, as human populations around other stars develop new technologies, utilize alien resources, and establish trade networks spanning light years. These interstellar economies would act as backups for knowledge, culture, and genetic diversity, helping Earth recover from future catastrophes or continue advancing civilization. The journey to Proxima Centauri represents more than travel. It marks humanity's evolution from a single-planet species vulnerable to cosmic threats into a spacefaring civilization capable of spreading life and intelligence across the galaxy. The technical obstacles are immense, the costs astronomical, and the time spans exceed individual lifespans. Yet the alternative is extinction. Humanity has traversed the immense void of space, endured radiation storms that would incinerate us, and faced energy demands surpassing our civilization's total output. Every mile toward Proxima Centauri uncovers new impossibilities seemingly designed to confine us to Earth. Within these challenges lies humanity's greatest opportunity to transcend its planetary origins. The same species that once feared the darkness beyond campfires has now sent robotic emissaries to every planet in the solar system, split atoms, decoded DNA, and created machines capable of thinking independently. What once seemed impossible often becomes inevitable when humans commit to making it so. The journey to Proxima Centauri will require solutions currently beyond human engineering and imagination. But perhaps that is precisely what we need. A challenge so vast it forces evolution, cooperation, and long-term thinking beyond current conflicts. The technologies we develop for interstellar travel will transform life on Earth, while the perspective of becoming an interstellar civilization will reshape our self-conception and future. In 4.22 light-years, a red dwarf star burns with the force of billions of nuclear explosions. And orbiting it lies a world that could become humanity's second home. The distance between here and there holds enough emptiness to swallow 1,000,000 solar systems, yet enough possibility to secure humanity's future among the stars. The journey to Proxima Centauri is not merely about reaching another planet. It is about preserving human consciousness, creativity, and compassion long enough to seed the galaxy with life and meaning. Subscribe and hit the notification bell because this epic journey has only just begun and the next impossible destination lies just beyond the horizon of our imagination.